right, hello and welcome. My name is Matthew Pete. Today I'm going to be talking about PIETOOLS 2021 and features of this software package which are relevant to time delay systems, analysis, modeling, and control. So PIETOOLS 2021 and 2020, of course, are very multi-featured. So they apply to modeling, control, and simulation of infinite dimensional systems, of which time delay systems is one particular application, but it's one which we've dedicated a lot of resources to. So let's begin the talk by getting started. So particularly how you get started. And how do you get started? Well, you download PIETOOLS. So how do I download PIETOOLS? So PIETOOLS has a nice website, first of all. So if you go over here to the website, you can see that we have several ways of downloading PIETOOLS straight from the website. So we've got the zip file, so you can just download the zip. Here we've got 2021A. 2021B is not on the website yet, but it will be soon. So you can download the zip, add it to your MATLAB path, and so forth. Alternatively, you can just download this script here, which does a bunch of things. So first of all, it downloads PIETOOLS 2021 and installs it. It also downloads Sadumi because you will need an SDP solver to run PIETOOLS 2021 because it is a meta parser. And it's got SOS Tools 3 in it. That's 2021A. 2021B has SOS Tools 4 in there, which you probably want to download instead. So I would recommend using 2021B. In addition, we've got several resources here. So we've got the user manual, which you can download. And I suppose we can take a look at that real quick. It's a rather lengthy and detailed introduction to all of the features of PIETOOLS, which we're going to be talking about today, and many more. So we can look at that. In addition, we've got a shorter YouTube video dedicated to PIETOOLS 2020 and a shorter version of the user guide dedicated to getting started relatively quickly and running some demo files. So if we go back to the presentation, those are all here. In addition, we of course have the GitHub site where the 2021B is currently located. We also have a MATLAB add-on manager package, so you can go to the add-on manager in MATLAB and also download it that way. So this is just a brief introduction to the structure of PIETOOLS. So your workspace as a DDE person will probably be dedicated to these two files, either the delay differential equation version or the delay difference equation version. So if you're doing neutral type systems, you're going to use this executive or this workspace. And if you're just using delay differential equations, you'll use the other workspace. In addition, we've got libraries of example files and demos. So in particular, the examples for the delay differential equation format are in here, and the neutral type and differential difference formulation are in here. In addition, we have a folder for the documentation and several other folders for utilities, which I'll talk about later in the talk. So things you won't probably mess around with are SOS Tools 400, which is necessary to run PIETOOLS, and the class definitions for Pi operators, which again I'll describe shortly. Now I'll just open up the PIETOOLS folder real quick, just so you can see where these things are. The workspaces for DDEs and DDFs here are in the root folder. The example files are here in the PIETOOLS examples. So here are the two example folders I mentioned. Demos are here, so particularly this demo here for delay differential equations, doing controller synthesis thing. In addition, we've got those converters, executives, and stuff I talked about earlier, and all these files which you're not going to mess around with. So going back. So to begin, let's talk about what PIETOOLS is. So PIETOOLS is meant to be an extension of the MATLAB toolbox for manipulation and optimization of pi operators, partial integral operators. So pi operators are an extension of matrices to infinite dimensional spaces. So that's the pi part, as in the number pi. The edible food part, the pi, partial integral equations, allows you to use those pi operators to represent and control infinite dimensional systems through using partial integral equations. And again, I'll talk briefly about all of these topics in a minute. So pi operators, what are they? So pi operators, partial integral operators, are an extension of matrices to infinite dimensional spaces. So if you may remember what a matrix is, a matrix maps Rn to Rn. So there's a matrix parameter here. But pi operators add several additional parameters to this. So they allow you to derive 4 maps, hence the 4pi name. So in particular, we've got Rn to Rn, which is here parameterized by a matrix. But these other operators are parameterized by functions. So in particular, we've got here L2 to Rn. That's this one right here, Q1. We've got L2 to L2, which is actually itself a pi operator. So it's got a pi operator parameter. And from Rn to L2 here is this function right here. So these are all polynomial parameters. This particular part of this particular parameter is itself a pi operator. It has 3 parameters within it, a multiplier parameter, where the multiplier is a polynomial, and 2 kernel integral operator parameters, where the kernels here define the subdiagonal part of the operator and the superdiagonal part of the operator. So 3 functions there parameterizing these 3 pi operators, hence their name. So pi operators are meant to be a extension of matrices, and as such, we've defined the opvar class, which allows you to manipulate and configure these operators as you would matrices. So in particular, once you've defined a pi operator, and we'll talk about how to do that later, you can do things like multiplication of these things, just like you can matrices, concatenation, transpose, addition, subtraction, and sometimes inversion if the operator is invertible. In addition, we have a whole bunch of other matrix-related operations which you may or may not think about on a regular basis, but they're all equally well defined for pi operators as they are for matrices. Now, that's the pi part of pi, not the edible food. For the edible food part, we are introducing the partial integral equation. So a partial integral equation is meant to be a universal representation of dynamical systems in infinite dimensions. So universal representation. So obviously we have ODEs, those are finite dimensional, DDEs, which are infinite dimensional, and then on top of that we have more general classes like neutral type systems, and more general classes like ODE PDs, or PDs coupled with ODEs. And all of those are contained within the general class of partial integral equations. So what is a partial integral equation? So obviously they're defined by pi operators, hence the PIETOOLS. So if we think about what state space is for ordinary differential equations, we have our standard 9 matrix representation of systems for ordinary differential equations, where we've got the state here, but in addition we have inputs and outputs. So in particular here's a disturbance input, and we have a controller input as well. In addition we have outputs, so a regulated output here and a sensed output. So this is our standard 9 matrix representation of an ODE. And the idea behind a pi is we extend this state space representation to infinite dimensional systems, which now act not just on Rn, but L2 as well. So all of these 9 operators are pi operators, and together they define a partial integral equation. With, in order to make this subset work, we have to actually add a pi operator here on the left, which makes things a little bit more complicated. So if you're familiar with singular systems, they sort of have the structure of singular systems. Occasionally we have to deal with things like this, where there's a derivative in the disturbance or the inputs. For most classes of systems you consider these operators are going to be 0, so we can mostly ignore them. So now we've got, from a 9 matrix representation of ODEs, a 10 pi operator representation of partial integral equations. And as we'll show, this allows you to represent all of these classes of infinite dimensional systems as pies. So the structure of a pie in the edible food sense in PIETOOLS is done term-wise. So we take each of these parameters for the system, which may or may not be defined, and you only define the ones which you're interested in. So the minimal amount of information you need to define a pie is the t and the a operator. So without that, there's not much going on. Everything else is optional. So if you don't define those other parameters, they just are assumed to be 0. So you can define as many terms or as few as you like when defining your pie. So, of course, the idea is we would like to be able to not work with pies directly, but take differential equations, delay differential equations, neutral type systems, and convert them to pies and then manipulate them that way. So, of course, we need a way of inputting our system into PIETOOLS in a way which it can be then converted into a partial integral equation. So let's cover that now. So, unlike pies, delay differential equations and neutral type systems can have lots of parameters, more parameters than you can in pies. Fortunately, for these parameters are all matrix valued, they're not operator valued, obviously. So in particular, if we look at a delay differential equation, this is sort of the more general form of delay differential equation, where if we look here, we just have the 9 matrix ODE representation. So if you didn't have any delays, you'd just start with this. Now, however, for each delay, we can add 9 more parameters. So again, mapping from inputs to outputs. And so we can allow delays in the disturbances, delays in the inputs, and of course delays in the state. So for every delay, there are 9 possible additional parameters. And if we include distributed delays in the mix, then there are 9 additional parameters for each of the distributed delays as well. And these parameters, in fact, can be functions. They can be polynomials. So again, similar to the pie structure, the DDE structure is defined term-wise. So let's consider a simple example where we've got a single delay differential equation here with one delay there, and we have a delay in the regulated output. Why do we have that? Just for academic purposes. So there are 2 delays here, one in the state and one in the output. And so the first step we need to do when defining a delay differential equation is define the delays. So we have a vector, dde.tau, which incorporates those 2 delays, the first delay and the second delay. So the dde.tau structure is almost always going to be used in a delay differential equation, otherwise it's just an ODE. But all the other terms are optional, so let's start with this one. There's no terms here, so we don't need to deal with that. There's one term, which is the delayed state. So we come over here, we see the delayed state. It goes to the dynamics, and so we're looking for that term right here. And so we define a dde.ai of 1 because it corresponds to the first delay. We just set it equal to -1. The next term, however, is an output term. So we look at where it's coming from. It's coming from x. And where's it going? It's going to the regulated output. And so which term are we looking at here? We're looking at this one right here. So we've got to define CI, C1i, and it's corresponding to the second delay. So we put the 2 there, and we set that equal to 1. And that's all we need to do. We don't need to define every parameter that could possibly exist. We just need to define the ones that we need. And then in the initialization routine, it sets everything else equal to 0. So this is just a list of the parameters in this DDE representation and what are the terms within the DDE structure which you can set, right? So in MATLAB. Moving on from the delay differential equation, we have a more general class of neutral type systems. So the neutral delay systems. The only real difference between a neutral type system and a delay differential equation is that we allow x dot to be present on the right-hand side. Note that we don't allow x dot to be present in terms of the current state, but only the delayed states. If we had this, this would be a singular system, and that's a different class of systems and has a different structure, which is difficult to represent. So we don't have that. We don't allow that. We do, however, allow everything else. So that's encapsulated in these E terms. So The other terms are the same as for the delay differential equation. The only new term we have here in this example is this E term. So it maps from there are two delays. It maps from the first delay to the state. So we're going to be looking at that term right there. So here's the normal ODE parts here and here. And now we have this E term, which makes it a neutral type system. And of course, we have to include our values of delay because otherwise we don't have a delayed system. So that's neutral type systems. And then the third in the hierarchy, the third class of systems in the hierarchy, is the delay differential difference equation. So a differential difference equation is sort of a stepping stone between the neutral and DDE types and the PI architecture. So what a DDF allows you to do that you can't do in a DDE or an NDS is identify structure in the delayed channels. So in particular, this R here is going to be of typically lower dimension than this big vector here. And you can't account for that structure in the DDE representation, and that's why we have to use the DDF as an intermediary before we get to the PI. So this, what's going on here is we have some output from the states, which goes into these delayed channels Ri. These Ri things are then the things that get delayed, and then output into the V, which comes back and affects everything else right here. So the DDF structure is more general than both the NDS and the DDE structure. And in particular, you can represent things you can't represent as an NDS or DDE, such as a difference equation. So here we have a simple difference equation where there's no dynamics at all. So, right, there's none of these terms over here. We just have a delayed channel, which is getting mapped straight back into itself. It gets mapped back into R, and then R gets delayed again. So how do we specify this structure? Well, first we specify our delays, of course. That's the first step. And then we specify how these R's are getting mapped to V. We just set them equal to 1. We're not going to be worrying too much about it. And then we see how this V gets mapped back to R. So R equals 1/2 times the first delay and 1/4 times the second delay. So there's that first term, and then we have a second term for the second delay. They're the same place. So the DDF, DDE, and NDS structures are rather flexible. If you want to see some illustrations or get a better feel for how you put these structures together, we refer to the example file. So we have these example files here for the DDEs are in this file, and for the DDFs and NDSs are in this file. So in particular, we have 25 DDE examples in this file and 15 NDS/DDF examples in this file. And they're all keyed to citations in the literature, or most of them are anyway. They're also grouped by type. So first we have the stability analysis problems with no inputs or outputs. Then we have H-infinity gain with some outputs. Then we have estimation with some sensed outputs. And then we have H-infinity optimal control, where we have a control input as well. These also have disturbances as well, disturbance inputs. So now that you've input your DDE, NDS, or DDF model, the time has come to convert it to a PI, or if you prefer, you can just convert it to some other format, but it's PIETOOLS, so we're going to focus on conversion to PIs. So how is that done? Well, as I said, there's a hierarchy to these models, right? So you can't, in general, convert a PI to a DDE. It's not possible, right? Because it's a more general class. You can, however, go the other direction, convert a DDE to an NDS. Well, why would you? Or a DDF, or an ODE-PD, or a PI. So we're not going to focus on this because this is not a talk on PDEs. So we have several scripts which do this. So for a DDE to a DDF, for example, we have this routine, DDE to DDF, where we emphasize the minimization. Because remember, the DDF has that structure which is not present in the DDE. And so in order to efficiently represent these DDEs, we have a routine which identifies the dimensionality of the delayed channel and represents that efficiently as a DDF. So we have an efficient DDF structure. You can convert directly to a PI, but it's not recommended, so please don't do that. The NDS, likewise, you typically first convert to a DDF, and we only even have a routine for converting directly to a PI. So all of these conversions pass through the DDF before they get to a PI. Likewise, if you have a DDF and you're not sure it's minimal, right, we have a routine to identify minimal channels, information channels. And then finally, of course, the DDF to PI is the workhorse here. And of course, you can convert a PD, but again, that's not the topic of this talk. In the end, however, you want to end up with a PI because that's where we can do the controller synthesis and observer synthesis and so forth. So just to illustrate a work-through, let's consider that neutral type system we had earlier. There's our neutral type system. First step is to initialize it. Honestly, that's done internally, so you don't really have to do that. Next step, convert that NDS to a PI. So there's our conversion routine. The input is that NDS structure, and the output is a DDF structure. So here was our original NDS, and then once we run this routine, we get a DDF, which is equivalent to the original NDF. So you can see it identifies the delay channels here. Next, we want to convert, of course, to a PI. We also do a minimization routine to make sure that we have making efficient use of those DDF structures. The PI, right, equivalent representation of both the DDF and NDS is given here. As you can see, it's defined in terms of two PI operators, T and A. So this is the A PI operator, and this is the T PI operator. So this is the 4 parts of the 4 PI operator, and then this 3 PI operator, which parameterizes the 4 PI operator, is given here. Those are the 3 terms, 1, 2, 3. So you can see the non-zero terms are 1, 2, 3 here, and 1, 2, 3, 4 here. So 7 non-zero terms, parameters in the PI, which is actually a little bit simpler than the DDF representation, which had like 1, 2, 3, 4, 5, 6, 7, exactly the same number of parameters. So now you've converted your DDE or DDF or NDS to a PI. The next step is, of course, to control it, or simulate it if you prefer. So for that, we have to talk a little bit about optimization, and this is really the raison d'etre of PIETOOLS, is linear PI optimization. So remember, our PI operators are supposed to be a generalization of matrices. So this is really a generalization of LMIs, linear matrix inequalities, to linear PI inequalities. So we're just replacing the matrix with a class of PI operators. So what's the reason for doing LPI optimization, the new LMI? Well, remember that the PI representation is supposed to be a state space representation for infinite dimensional systems. So whereas we had this 9 matrix representation of ODEs, here we've got this 10 PI operator representation of PIs. And because it's in the similar state space representation, most of the LMIs that were developed for ODEs generalize relatively straightforward manner to PIs. With, of course, the caveat that we got this T term here. So really, it's if you've got an LMI for a singular system, or a descriptor system, or a representer system, or however you want to label it, that's what you really want to convert to an LPI. So for example, we've got the stability criterion here, Lyapunov inequality, same as for an LMI, except we have this T operator here because there's that structure on the dot. And the dual Lyapunov inequality here, we got the H infinity gain, so this is a generalization of the KYP lemma. We've got H infinity optimal estimation, where we're adding a observer gain to our KYP lemma. And we've got H infinity controller synthesis, which is based on the dual of the KYP lemma, where in addition we have this thing here, which is representing our controller gains as well. So we've motivated the reason to have LPIs. And so now, how does LPI optimization work in PIETOOLS? That's the question. Well, let's start by remembering that any optimization problem has three parts. So there's the set of decision variables, the set of constraints, and the objective function. So for example, let's just consider that H-infinity optimal control problem, right? So we have three decision variables here. This gamma, which we're minimizing, P, which is our Lyapunov operator, and Z, which through a variable substitution represents our controller gains. So gamma appears there, Z is here and there. Everything else is data, right? It comes from the pi, in the food sense, partial integral equation. So those are our variables. Then we have constraints. So the constraints here are two. We have positivity of our Lyapunov inequality, or operator, and we have negativity of this KYP derivative, right? So we want to constrain this to be positive and this to be negative in the R cross L2 sense. So those are our inequality constraints. Finally, we've got an objective function. We're trying to minimize gamma, so that's relatively straightforward. So those are the three parts of our optimization problem, and how do we add them into our metaparser, which is PIETOOLS. So as I just said, PIETOOLS is a metaparser, right? It lies on top of SOS tools, which is itself, of course, a parser for Sudumi or whatever SDP solver you want to use. It takes advantage of the deep var and multi-poly representations of polynomials. And so it combines these three toolboxes. And as such, right, there are certain commands from SOS tools that we have to use inside of PIETOOLS. And so the first one is declaration of an optimization problem. So to declare an optimization problem, use this line. And for DDEs, NDSs, and DDFs, you don't change it, right? These are the independent spatial variables that the SOS program is going to use internally, and there's no reason to change them whatsoever. So in fact, actually, for single spatial dimension PDEs, you don't change them either. So this is, leave that alone. That's always goes into the header, the head of the DDE workspace. Second, we want to declare, of course, decision variables. Now, because PIETOOLS is a metaparser, you can use any of the standard variable declarations inside of PIETOOLS. Inside of SOS tools. Of course, that's not going to be enough, but you can use anything you normally use in SOS tools in PIETOOLS as well. And in particular, remember, we want gamma to be a decision variable, and gamma is not a pi operator. So it's a scalar, and so we want to declare it to be a decision variable using this SOS decision variable argument. Now, the SOS tool structure is such that once you've created this program structure, you have to pass it back and forth, but whenever you add a variable or a constraint. So you give it your current program structure, it adds that variable to it or that constraint, and then passes it back to you with that constraint. So you can actually create branches if you want to rename these things or something. So what about pi variables, right? So there's two types of pi variables, the positive ones and the indeterminate ones. So to create a positive pi variable, we use the pos lpivar command. And there's three mandatory inputs to this. First, of course, the prog structure, to which you will append the decision variable, which then gets passed back to you. Second, the dimension. Now remember, these are operators on Rn cross L2, and so you've got to specify the dimensions of Rn1 and L2 and 2, right? So those are the dimensions. And there's only two of them because it's a positive operator, it has to be square. So there's only two terms in there. The interval here for at least DDEs, NDSs, and DDFs is always going to be -1, 1, because once you've converted to a pi, it scales the length of that infinite dimensional state to be -1, 0. So this is always going to be, don't mess with that, it's always going to be the same. There are additional options which you can use help pos lpivar to figure out. And they can get rather complicated, but the simplest implementation is just this. So what does this return? This returns your prog structure, of course, with the appended variable, and it returns the P, which is the opvar, positive opvar, to the workspace so you can manipulate it using our standard opvar commands. Although it is not actually an opvar, it is now a dopvar, which is an efficient representation of the decision variables. So it separates the decision variables from the independent variables. It's a more efficient structure. So as a consequence, of course, you can't multiply a dopvar by another dopvar. Because, right, that would create bilinearity in your optimization problem. The second type of opvar decision variable is, of course, the indeterminate one. So there's a positive one and one which is not constrained to be positive. This one you can specify more dimensions. So in particular, remember it maps R cross L2 to R cross L2. And so you want to, in this case, specify the dimensions of both the inputs and the outputs. So there's 4 inputs to this one. I is exactly the same as before. Prog, of course, is the same as before. It just gets passed back. And this creates a opvar or dopvar in the workspace called P. Right. So positive and indeterminate variables. Next, constraints. How do we add constraints? So similarly, there's 2 types of constraints, equality and inequality constraints. So the equality constraints are relatively easy to declare. Say you want to set, say, AX equals F. Well, you create an opvar using P equals AX minus F. And then you set it to be 0 by just putting it into LPI along with the prog. And then it just returns the prog with that constraint appended to it. Right? So relatively straightforward. Inequality constraints, also relatively straightforward. Say you want to constrain A transpose X plus XA less than 0, right? You create a variable P equals A X transpose X plus XA, and then, well, you have to put a negative sign because you want it to be negative. This creates an inequality constraint, which is positive, a positive inequality constraint. So you just pass it the prog structure, it appends that constraint to the prog structure and passes it back to you for later use. Finally, of course, the objective functions, and again, this is a standard SOS tools command. So the input here has to be, of course, a prog structure, which gets passed to. And the second input has to be a scalar, right? A scalar, or at least mapped to a scalar, right? So it has to be scalar valued. Here it's just gamma, because remember, gamma was scalar valued. And so that sets our decision variable to be gamma, or our objective function to be gamma. And of course, this is minimization, so it's minimizing gamma. Then it just gives you the prog structure and you're done. Finally, to solve the problem, we use the standard SOS tools command, SOS solve, where there's an options input. And the options, at least now in SOS tools 4, include solvers, which were there before, but also, for example, MOSEC. So you can specify your SDP solver. And also there's a command for simplification of the resulting SDP, which helps in some cases, but not always, if you want to use that. So just to illustrate the work through for, say, the H-infinity optimal controller synthesis problem, we've outlined it here. So this is all sort of header stuff, standard stuff. So we declare these to be p-vars. Gamma is actually declared to be a dp-var because that's how you do it in SOS tools now. These independent variables, which then get passed into the SOS program structure and gives us an SOS program structure. Prog. We've created one. We now make gamma a decision variable using SOS decision variable. Gives us back our prog structure. Next, we create a positive Lyapunov operator, P. Here we've specified the dimensions of the R and the L2 spaces, and of this interval as normal is -1. And this gives us an opvar in the workspace. We then make it strictly positive, and this is important for Lyapunov operators. You have to make them strictly positive. And so we do that by taking that real part of the parameter, that matrix part of the parameter, and we add an epsilon I to it. And so that's particularly important and maybe non-obvious, so you might want to remember that. So we've added an epsilon I, where epsilon is some small value. Next, we create an indeterminate variable, which is z. So this is not positive, and as a result, we have 4 inputs to it. This is our input space, this is our dimensionality, is 0 dimension there. So this creates an indeterminate opvar z. Again, -1, 0, don't mess with that. Next, we create this big D matrix from the KYP lemma, right, which was on the previous slide. Just constructing it using the algebra of pi operators. And we set it to be negative semi-definite by making -d positive semi-definite. So that makes d less than or equal to 0. Next, we set our objective function to be gamma, minimization of gamma. We solve the resulting program structure. And finally, we get our solution. So we output our solution using getsol. So we output gamma here. We output the Lyapunov operator p here as well. And we output this indeterminate variable z. Now, we've got these p and z, and we can reconstruct our controller gains using zp inverse. So z, this is our standard k equals zp inverse, which we know and love from ordinary differential equations. And so now we have our controller gains, and we're ready to implement our controller. Now, many of these common LPIs, which are encountered in systems analysis and controls, have been implemented as executives. So stability analysis, dual stability analysis, H-infinity gain, H-infinity optimal estimation, and H-infinity optimal control. And actually, we have a dual version of the gain here as well. To make life even easier for you in the DDE workspace, right, we just created a bunch of toggles. So if you want to run one of these LPIs, you just set the corresponding toggle to 1, and it runs the LPI. And in fact, in the example files, there's usually an associated set of toggles you can uncomment, which apply to those particular problems, whichever it's grouped under. Finally, settings files. So in the DDE workspace, PIETOOLS DDE workspace, and PIETOOLS DDF workspace, of course, there's some scripts which will set the settings files for those executives you saw up there. So in particular, if you desire additional accuracy, you have a relatively medium-sized problem, you can use these heavy and very heavy settings scripts. Alternatively, if you have a very large problem, say 100 states or something like that, you probably want to use one of the smaller settings files, so the stripped or the extreme ones, if you want to reduce your computational complexity. The default is light, so that's what's going to run by default. Next, in at least controller synthesis, how do we implement our controllers, or our observer gains, if you will? Well, it depends on actually what your purpose is. So if you actually want to implement this in the real world, so it's a little bit more complicated, because what you've got to do is you've got to record the history, x of t plus s, and then, not just of x, but of w and u, and then you've got to construct these channels, because remember, we went through the DDF, and so this is a DDF implementation. So we've got to construct these DDF channels, and then we use those channels to construct V, and those V's go back to R. Now, what gets put into the controller, into the input? Well, the input is the current state of the system, and this partial derivative of the delayed channel as well, and multiplied by this pi operator. Okay. Now, of course, for most people, you're just going to simulate it. That's all you're interested in, and that's much easier. So all you have to do is just make a new pi, right? Pi dot a equals a plus b to k, and you're done, right? There's your new pi, t and a. And of course, you want to keep b1 in there as well. And then you just simulate it, and actually for the pi representation of a DDE or an NDS or a DDF, the real part of that state, remember there's a real and a distributed part, the real state is exactly the same as it was for the original system. So then you just plot that, and you're done. Right? If you want to get the history, you've got to reconstruct the state, but you probably don't want to do that. Don't need to do that. Which brings us up to simulation. How do you simulate these things in closed loop? So new with PIETOOLS 2021b, we do have an executive called PySim, which uses a very complicated simulation routines using Chebyshev basis functions, because of course, they're not intended just for DDEs or DDFs, which probably are better using forward and backward difference, but they work for all PDEs and PIs and DDEs. And so they're rather complicated. But a minimal implementation is not too hard. They take either a DDE or a PI input structure. So that's just the model structure. And then there's a couple inputs and a couple options. So the options are the number of basis functions to use. So that's accuracy. The time step also influences accuracy. The final time, how long you want to simulate it for, and there's several optional integration schemes you can use. In addition, you can specify the initial conditions here using symbolic variables. Don't get me started, symbolic variables are the bane of my existence. But at present, the input is in terms of symbolic variables, so you have to create symbolic variables. So sorry about that. Probably will be updated at some later release. Output is a solution structure, which is just basically the output as a function of time, not just of the real part, but of the distributed state as well. Right? You're probably only interested in the real part, however. So just to illustrate this, here's a controller synthesis problem. We've got the input, disturbance input here, and the control input there. We use that script, which you saw on the previous slide. We reconstructed the controller and we simulated it, and we plotted here the real parts. And this is in the DDE demo, in the demo file. And it outputs the plots. This is the open loop. You see it's unstable, goes to 10 to the negative 10 to the 9th. And this is the closed loop. I think this is a sinusoidal input. And you can see it rejects the input fairly efficiently. So to conclude, I just included here a list of things you can do in PIETOOLS for tourists. So if you're not interested in creating your own or doing anything very complicated, here's some things you can play around with just to get a feel for how PIETOOLS works. So number one, you can go to the example files, uncomment an example file, run it, see what happens. Is it stable? Is it unstable? They're all stable, but you can play around with that. Find the maximum value of a parameter. So play around with the parameters inside those example files. Right? See how large you can make your delay before it destabilizes. That's always fun. Or how it changes the H-infinity gain. Generalize an LMI. There's no H2 in there, so go for H2. Why not? See what happens. Change the setting files. See how the computation time changes when you change the settings file. Does it still run? Do you run out of memory? Probably not, depending on your size. The current PIETOOLS is pretty efficient, so you're probably not going to have problems unless you run, say, 100 states. So probably won't have a problem. But you can see how the speed of the solver changes as you change the settings file. Associated with that, in the example files, there are some scalable examples. So where you can specify the number of states. Sometimes they're academic, sometimes they're interesting. But you can increase the number of states until your system crashes. And let us know how many you got. Do simulation. Try that simulation, that PySim simulation. See, you got a DD floating around? Simulate it. See what happens. Convert something to a DDF. See what happens. Take that NDS you have, neutral type systems, convert it to a DDF. Bet you've never seen it as a DDF. Might be interesting. Take a DDE. Find a minimal representation. See how efficient your DDE structure is or inefficient it is at representing those delay channels. Can you make the delay channels much, much smaller? Usually you can. Finally, do some optimal control. Use that getting started demo I was showing you earlier. Run it. See how long it takes. Well, actually, honestly, the simulation takes quite a while. The controller synthesis, however, takes very little time. Finally, you look at those H-infinity gains. Play around with the parameters. See how the H-infinity gain changes. Compare the primal and dual H-infinity gains from the dual KYP lemma. They should be the same, but they're not always exactly the same. Usually because we truncate our degrees and one's more accurate than the other sometimes. They're all, of course, provable H-infinity gain bounds. And finally, if you're feeling extra adventurous, consider looking at PDs. We have a GUI. You can declare your PDs, play around with the structure. So finally, I'll conclude, I guess not with this conclusion slide, but I will open up the PIETOOLS workspace for you and just show you some things. So for example, here we go. Remember, this is the structure file here, right? Or the folder structure. There's that workspace, PIETOOLS DDE, PIETOOLS DDF. Here's DDF. We also got DDE over here. What's in here, right? Well, first of all, there's that parameterization, which I talked about. What all the parameters mean for the DDE and the DDF. Dimensions, things like that. Optional parameters, all this stuff. This is the example files. Uncomment that example file, run this command, and it loads the example. Simulation. So right now, it's simulating on. You can turn it off. It does take time for large problems. We're working on that. Here's those stability toggles. There's the settings file. Change the setting file if you want to change the settings file. Change your solver if you want to change your solver. Add the simplify command if you like. These are toggles. And this is just, these are for the binary toggles. It calls the various executives. But you can see how the executives are called as well. Example files. Here's the example files. They're grouped by stability analysis, gain analysis, optimal control, and optimal estimation. So here's the lots and lots of files. And here are the citations to them. So you can look at that. Here are the NDS ones, neutral type systems. There's 15 of them. Neutral type systems. And we have a couple difference equations in here thrown in for the mix. Those are under DDF. Those are listed separately. And they're both organized by stability and control problems. Finally, we've got the demo file. So that's in examples and demos, and the DDE simulation demo, which closes that loop, which we just showed in this talk. And it's taking a while, so I'll just move it over there. Yep. So initialize, convert, and of course we don't need to play around with it too. There are actually 3 possible problems you can run. So just uncomment one of them and run it, and it should do the controller synthesis in closed loop. So we can run that. Now here we go. It's like initializing there. That's what you see there. It's solving the problem. Here it's simulating. It's going to do open loop simulation first. Simulation does take a while because, again, not optimized for DDEs. And it uses that symbolic math toolbox. So it does take a while at the current moment in time. And it's simulating for 30 seconds. So it's simulated, 10 seconds. There's the actual optimal control problem. You see it ran in like a second. Doesn't take long. And then we found the closed loop controller, H infinity gain of closed loop 0.617. And again, we're simulating. Simulation, as I said, does take a while. I apologize for that. We will probably improve it in the future. And there we see open loop and closed loop. And you could switch the example file and run another case. So we'll close it up here. And thanks for watching. And I hope you play around with SOS tools and PIETOOLS when you get a chance.